Okay, y'all. So you decided to come over here and take a look at why we divide by n-1. All right. Totally awesome. Totally. It's a great question. I've thought about it for years. And I've tried for years to come up with a very slick, simple 2 or 3 sentence explanation as to why. I haven't found one yet, but I've got a pretty decent one, I think, that works well. Now, at the end of this video, if you want more, I'll point you to a page where I've actually proved all this stuff using algebra. But I don't think that's as telling as just looking at data and seeing what goes on. So what I've done here is I've created a population. And in this population, we've got 4 data values, 1, 2, 3, and 4. In the cells I1 and I2, I've placed the average of those 4 values, which is 1 plus 2 plus 3 plus 4 is 10, divided by 4 is 2.5. And I've placed the population variance. Now, you might recall the variance was the value that we had to find before we found the standard deviation. You find the variance first, and then you take the square root of that to get the standard deviation. So the population variance in this case is 1.25. And the way we did that was you take each of the data points, subtract the average, square it, add up all of those squared deviations and divide by 4. Okay? That's how you figure out what the population variance is. Now, because we're in a statistics class, we're likely never going to know those 2 values because those are parameters. We get samples that are drawn from the population. So down below this, I have listed out in this columns B, C, D, and E, every single possible sample I could from that population. The samples I'm choosing are of size 3. I was going to use size 2, but that was only going to be 16. If I used size 3, I end up with 64. I didn't want to use size 4, that's 256, and I was getting tired of coding at that point. So I just drew a sample of size 3 from this population. So my first sample is 111, my next sample is 112, my next sample is 113, and so forth and so on and so forth. All the way down. Here are all possible samples of size 3. Everywhere from 111 to 444. And some of you might be asking, wait a minute, why are you picking the same number more than once? Think of rolling a die. It's possible to get the same side more than once. Think about calling somebody in a survey. It's possible to get the same person more than once. It's not likely if you're drawing a small sample from a large population, but this is a small sample drawn from a small population, so it's actually very likely. So anyway, any of these 64 samples are possible. So what I want you to do now is forget about the population for a second, because you're a statistician. The only thing you get to look at is your sample. So what I've done here in column G is I've taken the average of the sample. So this first sample has an average of 1, since it's 1 plus 1 plus 1 divided by 3. This one has a sample of 1 1/3, because it's 4 divided by 3. Then 1 2/3, 5 divided by 3, and so forth and so on and so forth and so on. And you work your way down and you can see all the sample averages. The largest sample average down here is going to be a 4 when it's all 4s. There it is right there. So all the sample averages are between 1 and 4. And there's the distribution of all of them. Now what I've done under that is I've actually taken the average of all those sample averages. So if you think about that, what I did was I added all these up and divided by 64, because there's 64 of them. And the number I got was 2.5. Now that number might ring a bell to you. It's the same as the population average. So what that means is, on average, your sample mean is targeting the population mean. Now this is I'm going to drop a term on you here that you're going to learn again in Math 244. That means that the sample average is what's called an unbiased estimator of the population mean. You want those in statistics. You want to make sure that when you're sampling from a population, the number you're getting on average is close to the average in the population. Now, on average, the key is, of course, is on average. Some of these numbers are quite far away from 2.5. For example, an average of 1 is not that close to 2.5. An average of 4 is not that close to 2.5. But typically, on average, your sample mean is targeting the population mean. Now let's look at the sample variance. Now the sample variance is just the sample version of the population variance I mentioned up top. So what I did down here, I didn't actually use the formulas in Excel. I created the formulas from scratch. So in this column here, in column I, what I did was I actually literally did, and you can see the formula up here, I took each of the data points, subtracted the average from each one, squared the differences, added them up, and divided by 3. So again, it's the same thing we did on the board in the first few videos today, except I'm doing it in Excel, dividing by 3 instead of dividing by 3 minus 1, which was the formula in the sample variance that we talked about. Now, over in this column, the formula is exactly the same as it was in column I, except instead of dividing by 3, I'm dividing by 2. And then I copy those formulas all the way down. So this column is all divided by 3, and then the one next to it is all divided by 2. And you can see they're slightly different because you're dividing by, different numbers. You're dividing the same numerator by different denominators. So unless the number's 0, you're going to be getting different values. Okay, I go all the way down to the bottom, and what I did down at the bottom was I did the same thing I did with the sample average. I decided to take the average of all of those. Now, if we slide these up a little bit, I want you to take a look at something. This is the average of the sample variances I did when I divided by n, in this case 3. And then this is the average of the sample variances when I divided by 2, n minus 1. And you might notice something. You might notice that this matches that. Now, this might not hit you like it hits me, but you got to remember, when we did the variance in the population, we divided by the entire population size, n. But the sample variance, in order to match that, we have to divide by n minus 1. Now, some of you might be sitting there going, well, Sean, that's only because you chose the numbers the way you did. I mean, hell, you chose 1, 2, 3, and 4. Okay, so I've set this sheet up so that you can actually change your population if you want. So for example, I'm going to change this 1 to 9. Now if you do that, the entire sheet changes. Everything changes in the sheet. And it becomes a population of 9, 2, 3, and 4 with an average of 4.5 and a variance in the population of 7.25. So now, everything down here updates. Let's take a look. Once again, the sample average is targeting the population average. That's what we want. It's one of the reasons we actually study averages in statistics, is because this is true. Once again, the sample variance, dividing by n minus 1, targets the population variance. And the news is, it really doesn't matter what values you put in. The sample average is always going to target the population average, and the sample variance is always going to target the population variance. And because we have to stop at the variance first before taking the square root and moving on to the standard deviation, if we're going to be off with the variance, we're going to be even more off with the standard deviation. So this works for all values you could possibly put in here. I mean, hell, you could even be saucy and put a negative in there. It doesn't matter. Mathematically, this has to be true. Now, this is not a proof. This is simply a demonstration. It's a demonstration on a very small population with a finite number of samples drawn from it. I'm here to tell you, though, it holds for all populations. And if you want more, if you want to get lost in some algebra, on your 243 class page here, I've got a little page called Enrichment. And if you scroll down here to justifications, this is where my curiosity got the best of me. This is when I had to sit down and I had to figure out, okay, why is it that some of these things are why they are? What is going on? So if you scroll down right here, about halfway down, in class we used Excel to suggest the sample mean, sample variance, and sample proportion were unbiased estimators of their corresponding parameters. That sounds like gobbledygook, but this is actually for a 244 class. Here's a paper that I wrote up that tells you why X bar does a really good job of targeting mu, and S squared does a really good job of targeting little sigma squared. And it's just got some algebra in it. So if you're in algebra, you'll love this paper. If you're not into algebra, then you're going to maybe not want to look at that. But I just wanted to take you down that rabbit hole because that n-1 is not, it's not random. It's not an afterthought. It needs to be there. And there's a reason why statisticians were able to find that it was there. It has to do with that paper. Okay, so I hope that satisfied some of your curiosity. If I made your head hurt even more, I apologize. But we'll move on to a slightly lighter topic next class.